No, you're still muted, Nima. Are you?
Can you see my screen okay?
Yes, that's great, and we can hear you as well.
Okay, wonderful.
Okay, so take it away, Nima. Yep.
All right, well, I'm really delighted to be able to join, albeit virtually again this year. Hopefully next year we'll all get to see each other in person again. And I'm talking today on the day when there's all kinds of very interesting talks about positivity bounds, effective field theory, gravity, et cetera, which I'm really delighted to see all the fascinating work that's been taking place in this subject just over the past year. But actually, what I want to talk about is kind of something else. I mean, I myself started thinking about these things 15 years ago for an intense year where we thought about positivity bounds both in effective field theory and in the context of the weak gravity conjecture. And then again, around 5 years ago, starting with some discussions with Yutin and Jimmy Wang, which were motivated by sort of trying to discover string theory from the bottom up. And I even gave a talk at the strings meeting in 2015 about this kind of general program. And the program failed. It failed for an interesting reason. The specific thing we're trying to do failed, and the sort of consolation prize for the failure was the whole story of positivity bounds and the new nonlinear positivity bounds in the context of the EF dihedron and so on, which is sort of obvious given all the other sort of positivities that we've been seeing in the 10 intervening years since. But anyway, so that's the whole story of the EF dihedron, which for us was basically set by 2017, was a consequence of what was a consolation prize from something more exciting we were trying to do and we didn't manage to do. So I thought what I'd do today is go back and say something about first what those what that idea was that has a lot to do with really miraculous features of string amplitudes, some of which are well known, some of which are not as well known as I think they should be, and also because we've returned to this general subject over the past year with some really spectacular young collaborators, Lorenz Eberhardt and Sebastian Mazera, and have some new things to say about it. And that there's a general subject of thinking again about aspects of high energy scattering in string theory, which is also involves other work in progress with this cast of characters, as well as Pinaki Banerjee and my student Aaron Hill. So these are the things that I want to talk about in this talk. So first, part one is essentially the sort of story from 2015. Perhaps some of you remember this story, but at least looking at some of the participants, maybe many people haven't explicitly seen this story before. So I'll go through this part quickly, like just sort of motivate what's special about strings and how you might think that you could even discover strings from the bottom up. And that if you start doing the real magic, the kind of stunning magic is in checking the consistency even of the ordinary open string amplitudes. And the real magic is that of unitarity. We've been trying off and on to understand where that unitarity comes from directly. Of course, there's an indirect proof of unitarity. It's a no-goats theorem, but we're trying to understand, as you'll see, a very direct, simple mathematical question. And we've been stuck for ages until some really new ideas were brought in by our young friends. So that's what I'll tell you about in part two, is that there's a new contour representation of residues. This for 4-point string amplitudes. This representation is rather remarkable just on its own, just as an interesting object to study. It's something new about 4-point tree string amplitudes I certainly didn't know before. And amongst other things, it allows us to prove directly unitarity for string amplitudes, at least for less than or equal to 6 spacetime dimensions. So there's still some obstacles getting all the way up to 10 dimensions, but there's some real progress of a direct understanding of this unitarity. So that's the first aspect of thinking about string scattering, is genuine string scattering, high energy scattering in particular, for energies comparable to the masses of the string modes where we do this check about unitarity. Next, I want to talk about some of the most famous features of string amplitudes at high energies, which is that they're exponentially soft. But that anyone who's studied even the 4-point amplitude knows that they're exponentially soft in some regime, and exponentially growing in another regime. So it's not like some God-given thing that they're always exponentially soft, but remarkably, they're exponentially soft exactly in the physical Lorentzian regime and exponentially growing in some unphysical regime. And I've always been fascinated by this. Why are high energy Lorentzian amplitudes exponentially soft? Where does this business about the Lorentzian signature for the Mandelstam invariant sort of come in? So I want to say something about the general question of thinking about high energy string scattering, even beyond 4 points. Mostly I'll talk about just endpoints at tree level, but try to explain why high energy Lorentzian amplitudes are exponentially soft. And finally, if we have time, I want to say some things about some open questions in this general subject of thinking about Transplanckian scattering in string theory, also Transplanckian string state, and how it's related to the question of how strings morph into black holes as we go, string states morph into black holes as we go to very high. All right, so let's begin first with a sort of bottom-up tripping over strings. And I want to start with a very simple question that you might have even asked in high school. Why is it that gravity, which is the most obvious force of daily macroscopic life, is the thing that's hardest to UV complete, while much more hidden things like the weak interactions were discovered 100 years ago and UV completed in only 70 years? And the answer is that this is actually another aspect of the sort of famous UV-IR link when we have gravity. And let's contrast an easy to complete UV complete theory. Let's say we have the low energy amplitudes for pions. So low energy amplitudes for pions at leading order look like -1/f squared times s plus t. And even if you don't know anything about Lagrangians or Goldstone bosons or anything like that, you could or Maximum half potential, you could just try to UV complete this by just modifying the amplitude in such a way that it's softer at high energies. And so the dumbest thing I could do is just multiply by 1/1 minus s over m squared this term, 1/1 minus t over m squared that term, and see, okay, that's now something which is okay in the UV. It matches what we knew we had to have in the IR. And could this be the answer? And the answer is yes, it could be the answer. This is, of course, just a sort of linear sigma model, UV completion of the nonlinear sigma model. These are the Higgs poles. And to stress, I'll just be talking about here about tree level UV completion. So the only thing that we're going to imagine having is poles for the amplitude. But the crucial thing is that we can check for the sign of the pole at s equals m squared. The residue has to be appropriately positive, and it is positive. Okay. In fact, crucially, it's positive because of the minus sign out here in front of the whole amplitude to begin with. And in fact, if we didn't know about the minus sign to begin with, if we tempt this UV completion, we discovered that it only work with that minus sign. All right, so this is an example of how trivial it is to UV complete. We could have 1 Higgs, 10 Higgses. Okay, so this is a trivial sort of UV completion. And let's contrast this with another kind of theory. And this argument here doesn't per se have to do with gravity specifically. It has to do with the presence of long-range forces. And so I want to stress this part in an even simpler setting of just something like a phi cube theory. So imagine you have something like a phi cube theory. Now, phi cube theory doesn't need to be UV completed in 4 dimensions, but it does need to be UV completed in 7 or higher dimensions. And so you can again ask the same basic kind of question. We have an amplitude that the 4-point amplitude that dies as 1/s, and 1/s is not fast enough in high enough dimensions. So you might want to see if you can make it die faster. That's our game. We want to see, can we modify this amplitude so it doesn't go like 1/energy squared at high energies, but it goes like 1/energy to the 4th or a higher power. And if we attempt to do the same kind of idiot game that we did before, then we'll immediately fail because if I try to do the same thing where I put a 1/1 minus s over m squared, and similarly for the other channels, then you have a problem. The reason is that I'm no longer free to choose the overall sign. The overall sign out in front is actually controlled by the fact that there is a non-trivial IR pole, and the IR pole being positive fixes that overall sign to be positive, and therefore this thing that I've added is guaranteed to have a wrong sign pole, a ghost, that's something that violates unitarity. And it's easy to see this is a very general argument. Anything you modify, which is a rational function, only a finite number of with only a finite number of poles, and importantly, that where the residues in the S channel are just polynomials in T, so we don't include infinitely many particles at a fixed masses in S. you can argue that in any such function that you write down, the fact that the residues have the right sign on the massless poles implies that if you improve the amplitude at high energies, it must have the wrong sign somewhere else. And so the real issue is that if you have a theory that begins with a 3-point amplitude, so that the 4-point amplitude already has infrared poles, it already has massless poles, then it's impossible to come up with a tree-like UV completion with a finite number of particles. You have to have an infinite number of poles, and easy to argue, you also need to have an infinite tower of masses and spins. So we're already in the neighborhood of something that's stringy. And if we pursue this and now think about it in the context of now more specifically gravity, then something even more striking and simple happens. Let's start off with the 4-point gravity amplitude. Here it is for this particular helicity configuration. And there's something very striking about this amplitude, which is that the STU poles occur in a product downstairs, not as a sum, but as a product. This is, of course, the deep fact that there's no way of writing a gravity amplitude or a Yang-Mills amplitude. We're talking about gravity here. There's no way of writing a gravity amplitude as a sum over channels in a way that's manifestly Lorentz invariant. So we do get them as a sum over channels using Feynman diagrams, but then each term is not individually gauge invariant. We can write them as a sum over poles using spinor helicity variables, but we would have some reference vector that would correspond to something like light cone gauge. It wouldn't be manifestly Lorentz invariant. That fact that there's a product structure down there is a deep fact about gravitational and gauge amplitudes, which is related to the fact that when we use Lagrangians, we have to have gauge redundancy and so on to describe them. Okay, but anyway, there's a product structure down there. Now, we've just seen on general grounds, if you want to UV complete this guy, that we should have an infinite number of masses. And so let's just imagine writing down the same structure. And of course, no matter what we have, we can imagine putting on some giant denominator with some numerator. So we have some spectrum of masses here. And it's very natural that it has this product structure. Even, I mean, anything could be written as a product structure with some appropriate numerator, of course, but also the fact that it starts with the STU already in the massless limit makes this product structure natural. And now we have to demand that this numerator has to do a big job. Because if I go on a pole as S equals m squared, I will have residues that are not polynomials in T. So I want to kill these factors of T in the denominator. So therefore, this numerator has to have some zeros that kill these poles. And now, if you make the minimal ansatz that the only zeros of the numerator are there to kill those poles, then there's a two-line argument that I won't go through in detail here. There's a very simple constraint on the location of these roots, and the simplest that puts a constraint on the spectrum. The simplest solution to this constraint, if the mass squareds are linear in some parameter m string squared, and if you just shove that simplest solution to this ansatz into the formula, you get the infinite product form of the Virasoro-Shapiro amplitude. Okay, so that's by no means a derivation, but it's telling you that if you just do the absolute dumbest thing to try to UV complete gravitational amplitudes, you just run into the Virasoro-Shapiro amplitude. But if we go back to this question, we can look at that. We can look at that famous formula. And there's a natural question, and this is the question that Newton and I were asking back in 2015. Is it somehow possible that this is the unique weakly coupled, which means only poles, UV completion of gravity? And so that was the question. And one reason to suspect that this is extremely close to being unique is that the real miracle of this formula, the incredible miracle of this formula, is in the positivity of the residues. Okay, so if you actually check whether the residues at S equals n can be positively expanded in terms of Legendre or Gegenbauer polynomials, that residue, it's very easy to work out that the residue as a function of cosine theta at the nth level is a very simple polynomial in cos theta like this. It just has evenly spaced roots between minus n minus 2 over n and n minus 2 over n. And so the claim is that in order for even open string scattering to be unitary, you have to be able to expand this simple polynomial in cos theta as a sum over Gegenbauer polynomials, d-dimensional Gegenbauer polynomials of cosine theta with positive coefficients. Okay, and remarkably, this turns out to be true, but it's only true in less than or equal to 10 space-time dimensions. That should have been 10. D here is the number of space-time dimensions. So, and in fact, you already see this. This is actually an exercise in Polchinski's book. If you look at the first non-trivial level, n equals 3, you find that this polynomial is cos theta minus a third times cos theta plus a third, which is cos squared theta minus a ninth. And you just have to remember, this looks like spin 2 because it's cos squared theta, but the Gegenbauer polynomial in little d spatial dimensions is cos squared theta minus 1 over d. So this is cos squared theta minus 1 over d plus 1 over d minus 1 over 9. And so you see the spin 2 is there with a positive coefficient, but the spin 0, which is this 1 over d minus 1 over 9, 1 over little d minus 1 over 9 would be a ghost unless the number of spatial dimensions is less than or equal to 9, or the number of space-time dimensions is less than or equal to 10. Okay, so already the structure of the even open string amplitude has the information of the critical dimension in it. But what's really amazing is that this continues to be true for all higher levels. Okay, and it would be wonderful to have a kind of a direct understanding of why this is true. And I'm going to be telling you something about a more direct understanding of why it's true in a moment. But going back to our question, and this was the counterexample that we found a long time ago. So could it be that just imposing the consistency of massless scattering, the answer ends up being unique? And what we found in ancient times, the answer is no. And we found it, here's an example, but we found a class of deformations of the amplitude, which still have this gamma structure, but which you can deform in such a way that if the deformation isn't too big, you can inherit the highly non-trivial positivity of the usual string amplitude without spoiling anything else. Okay, so here is an example, and we find that if epsilon is not too big, if it's less than 1, you can use the miraculous positivity of the string amplitude and massage that fact to prove that even this deformed guy continues to be positive. And so if there is some kind of uniqueness, we also have to consider massive scattering. And maybe that's not unreasonable, because that's, after all, what happened in the story of the weak interactions, that we could imagine UV completing the 4 Fermi interaction through the exchange of a W, but then you have to also think about the scattering of the longitudinal W's in order to discover that you need the Higgs and to find the full UV completion. All right, so that was a story with U10. As I said, the whole story of the ftahedron was a sort of consolation prize from not being able to establish this, but I'm bringing it up again, A, to motivate what I'm going to be talking about next, and B, to say this problem is still there. And I think it's a fascinating thought that it might actually be possible to sort of derive this structure from the bottom up in some appropriate way. All right, so next I want to talk about something new, which is the unitarity of string 4-point tree amplitudes. And let's just remind you, we can be talking about open superstrings, closed superstrings of type 1 and type 2. And we have these, I'm going to call this, I'm going to strip off all the SUSY stuff, and I'm going to be focusing on the open strings up here. So I'll call that function A of S and T out in front. And if we look at the residue of this guy at the nth level, it's this residue polynomial, which is just what I told you about already before. Okay, so now written in terms of x equals cos theta. Okay, so and furthermore, given it's one of the many aspects of gravity equals gauge squared in string theory, the residue polynomial for the closed strings is just a square of the residue polynomial for the open strings in this case. Now the claim is that the open string residue, so if I just take this polynomial, I can expand it in Gegenbauer polynomials with positive coefficients for a capital D less than or equal to 10 space-time dimensions. Okay, so that's the claim that we're going to try to understand better. And once you know that this is true for the open superstring, then the positivity for the closed strings follows trivially from this. That's because the positivity of the closed string residue is a square of the open one. And if you have any function that's positively expanded in Gegenbauers. If you take the product of them, it's also positively expanded in Gegenbauers. That's trivially the fact that spin 1 times spin 2 is decomposed into a sum of other spins, all with positive coefficients. All right, so this is the thing that we're going to try to understand. And of course, there's already an indirect proof of this fact, which is the no-ghost theorem. Okay, but it's such a very basic seeming statement that we'd like to have a better understanding of it, possibly more directly if we possibly can. Okay, so now just to look at some examples of what it actually looks like, here is just some examples of what those coefficients look like for the different string levels. N equals 1, 2, 3, 4, 5, and different spins, j equals 1, 2, 3, 4, and so on. And you notice this clear pattern that so this has got the guy that we're just talking about. The critical dimension is d equals 10 here, but you get some interesting expressions. And again, the claim is that all of these expressions are positive if d is less than or equal to 10. Another comment to make at this point is that you can see this alternating structure. The residue vanishes when n plus j is even. So another way of saying it is at the odd levels, the residue only exchanges even spins. At even levels, we only are exchanging odd spins. And this is a consequence of a world-sheet parity. Okay, oops. Now, what are we going to do? We're going to, in order to try to understand this, we're going to try to extract these coefficients using the orthogonality of the Gegenbauer polynomials. Okay, oh, sorry, I forgot to multiply this by the residue function of x here, but this is the so after I multiply this by the Rn of x, this will extract the coefficients of n and at level n for spin j. All right. Okay, now there are two easy limits here where it's easy to see that you have positivity. The most trivial one is when j is close to n. For example, when j equals n, literally, or j equals n minus 1, that's the sort of highest spin. You can see that starting at j equals n and higher, the residue just vanishes. And it's trivial to see that the coefficient of the highest Gegenbauer must be positive simply because it begins with a leading term, which is cos theta to the n minus 1. Okay, so given that that coefficient is positive, you know that you're going to pull out a positive coefficient in front of the highest spin guy. And by following that kind of argument iteratively, you can subtract the highest spin and then do some analysis for the subleading. Of course, it gets harder and harder when you do it that way. But in principle, you can see that you have positivity close to j of order n. It's also quite easy in the opposite limit when j is fixed and n is large. And in order to see why, if you just plot what this residue polynomial looks like, we just go back for a second. So you see that this polynomial has evenly spaced roots between n minus 2 over n and minus n minus 2 over n. And so when x is close to 1 or minus 1, it's not small, but the second x gets closer than the second x goes into the interior, I have the product of order n numbers that are all smaller than 1, and so I get something just exponentially small. So Rn of x is something that is really peaked at the two ends, at x equals minus 1 and x equals plus 1. And therefore, if you integrate that against some Gegenbauer, like g0 of x, which is just something flat, then this is going to be dominated by the two ends where the residue is positive. Okay? And so that's how we can see that, for example, the spin 0 residue, it's very easy to see that it's always positive for large enough n. Of course, it's a spin 0 residue that gives us a constraint of d less than or equal to 10 at low levels, but it's easy to see that when the spin is fixed and you go to high n, things get dominated by the endpoints and you have positivity. In fact, if you just plot what these residues look like, this is actually what they look like. So if I look at beta n and j for some dimension less than or equal to 10, it starts off as something positive here. Again, it would go to 0 and d equals 10. Some scalar coefficient would actually go to 0 here. But when d is less than or equal is less than 10, it starts off as something positive. So out here, we can easily see that it's positive. Way out here, we see when j equals n minus 1, it's trivial to see that that's positive. And if you actually plot what it looks like, it looks something like this. It actually goes up and then goes down, and here it just goes, of course, close by, just goes linearly. It peaks at around j of order to the square root of n, and then it dies exponentially, even slightly faster than exponentially on this other side. So it's kind of ironic that it's easy to prove positivity over here and out there, but in the middle where the answer is actually bigger, it's very hard to directly prove positivity. And you can take all kinds of sort of direct formulas where you do these expansions. There's many different expressions you can try to write down for these residues. They all have alternating signs in them. It's just not at all clear why the answer is positive. So there needs to be a new idea in order to get some inkling for why the answer is positive. And that's the new idea that I want to tell you. So this idea actually begins with something which is not directly about positivity, but something I think in a sense even more striking, that there's a direct and rather beautiful contour integral, double contour integral representation for these residues. And this is the formula. I'll tell you something about how it's derived in a moment. Okay, but let's just we're going to just take it as a given for a little while and just show what we can do with it. So there are these variables u and v. There's this sort of interesting, relatively simple gadget in the integrand here, and this is a double contour integral formula around 0, which is really just saying that we're taking iterated residues. So that's really saying that this object has a Laurent expansion where you first expand around v equals 0, then you expand around u equals 0, and you pick out particular terms in the Laurent expansion that actually give us this residue, that give us this coefficient. Just a tiny bit of notation, you might have seen I switched between this beta and b. The capital B is just pulling off some overall positive factors that have to do with the normalizations of the Gegenbauers and so on that we don't want to drag around. Okay, so they're just positive prefactors. So this is a slightly simpler thing to be looking at. Okay, so that's the thing to think about, is that we have this iterated residue here. And now if we take this expression as a given, again, I think the most remarkable thing is that such an expression exists at all. And given, for those of us who played with this object for a long time, the kind of biggest frustration was that while the gamma over gamma, came from Euler or came from Veneziano, that has some God-given purpose in life, the act of expanding it in Gegenbauers just seemed like a totally artificial thing. And it didn't seem like there was anything natural or beautiful or canonical about it at all. And yet there appears to be. So this very beautiful and simple formula is directly an expression of the residue. So there is something nice about these residues after all. In the next few slides, I will show you how this gives us a direct proof of positivity of the residues for d less than or equal to 6 space-time dimensions. And another application is that it lets us understand the asymptotics of this of these residues. So we understood something qualitatively about these curves, but we understand something more quantitatively about what it looks like in these waves. Okay. All right. So first, let me tell you how you get positivity. You begin with this contour integral expression, a sort of small natural change of variable from u and v to x and y by a u is log 1 minus x and v is log 1 minus y gives you this expression. So just shoving it into the previous contour integral formula, it gives you this expression. And remember, these integrals around y equals 0 and x equals 0 are just telling you to Laurent expand this in y, pull out the coefficients in x, and then pull out the coefficient of 1 over x in the 1 over y coefficient and the Laurent expansion of the y-dependent part. Okay, and why does this make positivity manifest? The reason is that it's easy to see that this expression, that there are 3 terms here, 3 factors. Each one of them, one can relatively straightforwardly see have a manifestly positive Laurent expansion in both y and x, never mind pulling out the actual particular Laurent coefficient that's needed for the residue. So that's particularly obvious for this guy, 1 over x minus y. If we imagine Taylor expanding in y first and then in x, clearly this is just 1 over 1 minus y over x to some power. 1 over 1 minus y over x is 1 plus y over x plus y over x squared, and so on, all plus signs. These other expressions are slightly less obvious that they're manifestly positive. They don't, on the face of it, immediately look manifestly positive. But they are for relatively simple reasons. So the positivity of the rest follows from facts of this sort. In fact, these are all the facts that there are, that these interesting little expressions, 1 over z plus 1 over log 1 minus z. Let's start with this guy. That guy is not, again, trivially positive. If you shove in the Taylor expansion of log 1 minus z downstairs, there's alternating coefficients. When you invert it, it's not obvious what all the signs are, but this combination has all plus signs. And then they're closely cousins of them. This combination has all plus signs. And this combination, where you allow more powers of log 1 minus z downstairs, also has all plus signs, but only when the number of powers is not too big. Only when this alpha is less than or equal to 2. That is where our restriction on d less than or equal to 6 comes from. That's why we can't yet prove things manifestly for d greater than or equal to 6, because that coefficient here is this d minus 2 over 2, and we have to have that d minus 2 over 2 is less than or equal to 2 in order to have manifest positivity. That's where capital D less than or equal to 6 comes from. But anyway, the claim is that all these expressions have positive coefficients in their Taylor expansions. And so let's take a simple example. So if I take this f of z, which was 1 over z plus 1 over log 1 minus z, there's a number of ways of proving that this has a positive expansion. You can, for example, just multiply it by z and do and recognize it as a very simple integral. Now, if I take m derivatives of this guy at z equals 0, I can take the derivative inside the integral and just manifestly see that it's the integral of something positive. So that's a very mechanical way of seeing that it's positive. Another way of seeing that it's positive for large enough coefficients is I can extract the coefficients in the Taylor expansion of f of z by doing a contour integral around z equals 0, dz over z to the m plus 1. So there's the contour integral around 0. But as usual, I can deform the contour to go around the branch cut of this 1 over log 1 minus z. And now something slightly amusing happens. When you deform it there, I get the discontinuity of 1 over log. Now, we're all used to the fact that the discontinuity of log is 2 pi I. But the discontinuity of 1 over log is an amusing function. It's 1 over L minus I pi minus 1 over L plus I pi, which is just 1 over L squared plus 1. The pi's cancel, and you get an integral of something that is, again, manifestly positive. So that's the style of argument that also works for all these other functions, again, if alpha is small enough to prove they have manifestly positive expansions. So, for instance, how do we use this to prove that all these things are positive? Well, this factor, as I said, is trivial. These factors are essentially those functions, h alpha, that I just defined. So these have manifestly positive expansions if d is less than or equal to 6. This is manifestly positive. The last remaining thing is this little guy, and that little guy is also positive, beginning with the fact that f of z has a positive expansion. So I write it as a sum of cm, z to the m with positive c's. And then I can just recognize this 1 over log 1 minus x minus 1 over log minus y as the difference between f of x minus 1 over x minus f of y minus 1 over y that has a positive piece and a sum with the positive coefficients of x to the m minus y to the m over x minus y. And happily, this guy from junior high school, we know it's just a geometric series, x to the m minus 1 plus x to the m minus 2y plus dot dot plus y to the m minus 1, all positive coefficients. Okay, so this contour integral representation, together with very straightforward, if not 100% obvious, relatively straightforward positivity statements about these functions, lets us prove that all the coefficients are positive. Now, that's for d less than or equal to 6. This form is not useless when d is less than or equal to 10. It just means that you have to do a little more work. So at any fixed j, a finite amount of work is needed to prove positivity for any n, so long as d is less than or equal to 10. But we still don't have a direct proof for all j of positivity for d up to 10. Okay, so another application, which I mentioned, is something about asymptotics. So there are two natural regimes that we can take. J is fixed and n is large. I apologize, there's a 1 over missing in this formula. But the only place where n appears in these residue formulas is in this x minus y to the n. And so clearly, if I'm going to large n, I have to pick out the highest power of y in the expansion of this guy. So that simplifies the contour integral. I can just pick out the highest power of y and take out one of the integrals. I'm left with one more integral as a contour integral that I can deform a la the sort of Hankel contour, which is familiar in the analysis of the asymptotics of the gamma function, and that gives rise to a concrete formula for these residues, again at large n and fixed j. Okay, and again, it grows linearly with j, and it falls off basically as a power of d with a logarithmic modulation. Another limit that we can take is the Regge limit, where we go to large n, but where n minus j delta is fixed. So these would be an expansion of the Regge trajectory. Sorry, not the Regge limit, but for a fixed Regge fixed order of descendant. That's this capital delta. And for this form, it's useful to go back to the UV representation of the residue. Again, the only dependence on n now with delta fixed comes in this exponent. And once again, at very large n, in order for this not to be exponentially crushed, the integral is dominated in the neighborhood where v is close to u. And again, you can do an analysis and get this form for the asymptotics. And again, dies exponentially in just the way that we saw from this qualitative picture. But now we have a more quantitative understanding of what the residues look like in this limit. This was a limit with j fixed in large n, and out here close to the end here at a fixed delta over it, where it's dying exponentially, is the asymptotics from the second form. Okay. Now, that was all for the open type 1 superstring, and there's general formulas for the residues for all the string theories. So for general open string residues, it has this same general kind of form. There's just an extra interesting exponential factor that we didn't see there before. So a equals 0 for the type 1 superstring, but this a is equal to 1 for the bosonic open strings, but otherwise very, very similar form. And we can have closed string residues for type 2 and for the bosonic string, and heterotic residues that again have an interesting form of a triple contour integral. Obviously, they trivially have a quadratic contour integral. Well, actually, not obviously. In fact, that's what I wanted to say. The residue polynomials are the squares, but it's not obvious how to extract the actual formula for the residues from the fact of the closed string residues are the square of the open string ones, and the heterotic ones are the product of the bosonic residues and the superstring residues. But it's not trivial how to extract the actual coefficients from that information. And interestingly, they're naturally given as triple contour integrals, not quadratic contour integrals, but they're really naturally given as triple contour integrals in this way. Okay. All right. Now, so far I didn't tell you where this formula came from, so I just want to say a few words about where it actually came from. And you're not gonna, I'm not expecting you to digest this in real time, but I just want to give you an idea of the sort of basic moves that go into the derivation, because there's one place where something sort of remarkable happens, and I at least want to highlight where that is. So we begin with the formula for the amplitude, just given in the usual beta integral way. And so the residue of this at s equals n is just given by doing a contour integral around dividing this thing by z to the n, exactly as you'd expect. Okay. But now we have to take this guy and integrate it against the Gegenbauer polynomials. And we're going to use the Rodriguez formula for the Gegenbauer polynomials. This is a classical fact that writes the Gegenbauer polynomial as, roughly speaking, the jth derivative of something. So the jth Gegenbauer polynomial is the jth derivative of this interesting curve. And if you put these two things together, you get a direct formula for this residue, which is given by this expression. So this guy here, remember x its cos theta is related to s and t by the usual formula. The t is s halves times 1 times cos theta minus 1. S is equal to n over 2. So we're just trading cos theta for t in writing this form. Okay, so this part is the Rodriguez part. This part is the residue part. All right, so that's the sort of expression that we're looking at. And this integral from minus n to 0 in t just corresponds to the integral from minus 1 to 1 in cosine theta. All right, so now we're going to call this expression p of 0 minus p of minus n, just clearly because there's some indefinite integral that has two endpoints, 0 and minus n. And so you just do a few obvious massagings on this object. You don't need to study this in any detail. But now, having put it in this form, two remarkable things happen. One of them is that you recognize that this function, p of t prime, can be recognized as that this integrand can be recognized as the total derivative. And two, there's an interesting symmetry between p at minus n and p at 0. In fact, p at minus n, that's the difference that we care about here. But it turns out that p of n is actually equal to p of 0 when n plus j is even. That's the explanation for why the residue vanishes when n plus j is even in this direct computation. But when n plus j is odd, p of minus n is just negative p of 0. And so therefore, this difference that just shows up is just up to a factor of 2 given by p of 0. All right. So those are the that expression for the for p of t prime as a total derivative is an interesting identity. It's an interesting identity that allows us to move forward. And okay, I could just either show you the identity, just keep on going with the derivation. After all, it's just an identity, but it's the kind of at the heart of what is going on. And so we've been trying to write this fact in a number of different ways. And at least to me, the most evocative way of writing this identity is to notice an interesting kind of duality. In other words, it's an equality between it's a relationship between the generating functions for two different objects, where one of them is the Fourier transform, or better yet, one of them is the Laplace transform of the other. And so one object is made out of the things that we just saw. Okay, so even if you don't see it in any detail, you see that we have these j derivatives with respect to something in this Rodriguez formula. Well, we have something that looks like that here, this 1 minus dx squared to the j. Okay, so this is the way, as you're just straightforwardly doing the residue calculation, this is the object that you run into. And if you make a generating function out of this for all j, I'll call this a function of t and x. Okay, there's some nice generating function for this guy. But there's a second set of objects. These are what turn into the total derivatives that I mentioned before, which are these guys instead, which are manifestly j derivatives on something. You build a generating function for the second set, and the kind of basic phenomenon, the basic identity is that the generating function for these capital P's are the Laplace transform for the generating function of the capital Q's, which in particular gives you a way to relate this expression to that one, obviously. Now, there's various ways even of motivating this fact. I won't go through the motivations for it, but I just want to sort of sketch how you go from this basic fact to the double contour integral representation. We can begin essentially with the formula that we had a moment ago, slightly rewritten for the residues. Again, this is what happens if you proceed in an obvious way. You haven't noticed anything sort of remarkable. Nothing miraculous has happened. But then this equality between this identity I mentioned a second ago allows you to trade this object, which appears here, for j derivatives of something, and that lets you do these integrals now. Now I have to do this. I have to do this integral. That now lets you do these integrals, because this is now j derivatives. So I can integrate by parts j times to put it in this form, and now I have j derivatives acting on something else. But I can write those j derivatives or j plus something derivatives acting on something else as a residue integral by introducing another variable v. And after you do that, so those are the steps. There's this interesting identity that after you do integration by parts, lets you recognize an integrand with the J derivative with respect to the integration variable that you in turn express as a contour integral. So that's what gives rise to this final contour integral representation. I'm sure you didn't absorb any of this in real time. You weren't expected to. But one thing that I want to stress is that it's not at all clear in this set of manipulations that we should have ended up with this very symmetrical looking expression between U and V. U, after all, was one of the variables that we started off life with. It was part of the integrations that defined the beta function to begin with. This V is just some auxiliary thing that we brought in at the very end of the calculation, and yet at the end there's this beautiful expression which has this perfect symmetry between U and V. Note it's not entirely symmetric because it's very important in this formula to do the integral over V first, and then to pick up the residue at V equals 0 first, followed by the residue in U. Obviously, since it's symmetrical, you can do it the other way around as well, but there is an ordering between them. So the final expression as a double contour integral has the remarkable symmetry between U and V. Why? We don't know. And clearly, the fact that there's such an expression at all, as I was trying to stress, is a surprise. Certainly, I didn't expect there to be any such simple expression for the residue. So where is this expression really coming from? There should be a much more conceptual understanding that does not involve this set of very clever manipulations and observations. So it's begging for a much more conceptual explanation and derivation than the one that we have so far. All right, so now that's all I wanted to say about that. Am I out of time at this point, organizer? I don't remember how long.
Slightly, Nima, yes, but what I would say is, given that it's getting quite late here in Europe, if you want to get any important points out the way now, you're welcome to go on longer, of course, if people want to stay and listen.
Right. Well, I think I can say what I can say. Maybe I'll go on for just 10 more minutes. I have a very simple point to make for part 2. So, or alternately, we could stop and clap now. And anyone who wants to disappear is free to disappear now.
It's certainly fine by me to go on for another 10 minutes, but
okay, let's continue then. Okay, so all right, so the next sort of qualitative thing that I want to talk about is why are high energy amplitudes in string theory, why are they soft in the Lorentzian regime? Oops. Can you guys see my screen?
Yes.
All right. I can't see my screen, unfortunately. Hold on a second. Yeah, my laptop just died, so it's very interesting. Okay. Hold on a moment. Let me stop sharing and see what happens. Maybe my laptop is trying to get me to shut up. That's not the first time. It's not the first time. Either that or someone out there has hacked my laptop in order to get me to shut up. Just a moment here. I don't exactly know what's happening, but I cannot see my own screen. Okay, I think that is better. All right, now at least I can see my own screen. So let's try this again. All right, good. All right, can you see my screen now?
Yep.
All right, good. Sorry about that. So I'd now like to ask this question: why are high energy Lorentzian amplitudes in string theory exponentially soft? And let me remind you, we have these kind of first. I just want to make a general point that we have these integral expressions for amplitude as a function of S and T, or ST and U for open and closed strings. And I think we should be very unhappy about these formulas. These integral expressions are only convergent. For example, the open string expressions are only convergent when S and T are negative, not the physical region. And in order to just see what happens in the physical region, to even decide whether it's exponentially soft or not, and so on, involves some analytic continuation. It's even worse for closed strings, that these expressions are only convergent for a finite region in the ST plane. So once again, in order to analyze what happens at high energies, even in the unphysical regime, you have to do some analytic continuation. And your attitude might be, some people's attitude is, well, the integral is true, and we have to analytically continue. So what? My attitude is that you shouldn't have to do work when you understand the sort of the physics correctly. You shouldn't have to do any work. The object you're studying should just tell you what the answer is without any work. And so, in my view, this sucks very badly indeed for the greatest UV complete S matrix of all time. And in particular, if you wanted to know the answer, I don't know, you have like 6-point closed string scattering, where we don't have the analytic formula in terms of gamma over gamma, and so on. And some experimentalists might just want to know, what's the actual amplitude in my physical experiment in some region? You can't do it, without doing the analytic continuation. You can't just put it on the computer and press return and get the answer. I think this is very bad. This is some indication that we're not understanding the S matrix for string theory properly yet at all. But in any case, at least at 4 points, we know the answer, that it dies exponentially when S is positive and T and U are negative and cyclic. In other words, it dies exponentially in the physical Lorentzian regime, but it grows exponentially in the unphysical regime where all those signs are reversed. In fact, there's a beautiful paper by Simone and Zohar and Amit and Sasha, where they even talked about some universal behavior of the exponential growth and universal Veneziano-like behavior of exponential growth given any kind of consistent UV theory. But it was exactly in this regime where the amplitude grows exponentially. So it's not true that the amplitude dies exponentially everywhere. It dies exponentially somehow only in the Lorentzian regime. And I've always found this fascinating, that even though these expressions don't seem to care about Lorentzian kinematics, somehow the analytic continuation does, and it knows that it's exponentially soft in this Lorentzian regime. So I'd like to understand that. And so despite the fact that these integrals have to be analytically continued, blah, 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 we're not going to do that explicitly. Instead, we're going to just look at the high energy saddle points. This is very, very familiar. And then if we understand something about the high energy saddle points, then we defer to later the discussion of how you imagine deforming the contour, et cetera, to go through the saddle. But if the behavior of the saddle points is nice enough, we don't need to worry about that too much in order to actually decide whether the amplitude is exponentially soft or not. So the high energy saddle points are just governed at tree level by the saddles of the Kobe-Nielsen factor, which we can write as e to the minus alpha prime times some action, and the action is sum over ij, Fij log zi minus dj, and the critical points are the Gross-Mende or the scattering equations. Okay, so when we study this at 4 points, these are the scattering equations. They have this one solution, z equals s over s plus t. Again, note that in the physical region where s is positive and t and u are negative, not between 0 and 1. So it's not on the contour of integration. Nonetheless, if I look at the real part of the action for n equals 4, it's this s log magnitude of z plus t log magnitude of 1 minus z after I take the real part. So if I shove in this expression for z, there it is, and you can verify that this is indeed positive when you're in Lorentzian kinematics. Okay, but it's something you just verify. You check that it's positive in Lorentzian kinematics. Now, this action for tree amplitudes has a very important role to play in the high energy limit of string amplitudes, because Gross and Mende argued in the late 80s that the real part of the action at L loops is in fact proportional to the tree amplitude, but is proportional, but is actually smaller, and it's 1 over L plus 1. And this is the ultimate reason. So that means as you go to higher and higher loops, even at weak string coupling, an L of order the energy over n string is the order in the loop expansion that actually dominates. And so while the tree amplitude goes like e to the minus energy squared, that drops so quickly that these other saddles at higher loops become more important. And the actual amplitude goes roughly like e to the minus energy over n string. You can argue it's really e to the minus energy over m string log energy, but anyway, at zeroth order, it's something like e to the minus energy rather than e to the minus energy squared. And it's exactly the same action which shows up at loops. All right, well, now we'd like to ask an obvious question. What happens for endpoint scattering? And again, why was Lorentzian kinematics special? I mean, here we didn't really have to, we could just check that it was positive for Lorentzian kinematics, but still, why did it turn out that Lorentzian kinematics was a special? And so we'll do this analysis at tree level. So again, we'll just define the action to be the sum of Sij log the magnitude of Zi minus Zj. So this is really the real part that I was talking about before. Let me just define that to the action now. So there's critical points of this action are the solutions to the scattering equations, but there are n-3 factorial solutions of these guys, as we know in general. So the obvious hope is that the reason why the amplitude is exponentially soft is that the action will be positive on any one of these n-3 factorial solutions. Let's say it turned out that it was only positive on some of them. That would be kind of a disaster because you'd have to argue why only those saddles contributed when you did the deformation and so on. Life would be much more complicated. The obvious hope is that the action is just flat out positive on every one of the n-3 factorial solutions. So long as the Mandelstam invariants, these little Sijs, are Lorentzian. And now you can try to do this directly, but clearly proving this directly seems very, very difficult because the scattering equations are complicated and the roots are complicated. So it's going to be very hard to do the analog of what we did at 4 points, which is explicitly solve and plug in to verify to understand why it's true. So that should be a simpler reason for why it's true. And there is, in fact, a very simple proof, really a trivial proof. You begin by writing a classical closed string solution. So x mu of z and z bar is the sum of pi mu log the magnitude of z minus zi. Again, the magnitude there is important. We're going to imagine that the momenta are real, but we're not saying anything about the signature. Okay, so we're not saying anything about the signature of eta mu.
Yeah, there's a problem with your audio. We think it's on your side, or at least I think it is.
Okay.
It's better if you lean forward, or I'm not sure what the problem is.
Can you hear me?
I can hear you, but it's been getting worse.
It's been getting worse. All right. Well, let's see.
It's been like this for a while.
Okay. Sorry about that. Well, is that any better now or no?
No, it was better. It was better 10 minutes ago. Before that.
It was better 10 minutes ago. All right.
Yeah, before the chaos.
Before the chaos. All right. Well, probably related to the chaos. Sorry. It's probably related to the. I'm sure it's related to the chaos. Hang on 1 second. Maybe I'll try leaving and rejoining. Is that okay? Just give me 20 seconds. All right. Let me try that.
Plus, we need a break.
At some point, we should probably let Europe go to bed too. No.
Well, I think they can just go. The Europeans.
Yeah.
He opens up quickly.
Is that any better, guys?
Yes.
All right. Sorry about that. I really have no idea what the hell's going on, but I do need to be allowed to share my screen, though.
Oh, hold on. It's definitely a lot better now.
All right. Sorry again. All right. Can someone allow me to share my screen?
Hey, 1 second.
Oh, sorry about that.
Now you should be able to do.
All right. Thank you. Thank you very much. Sorry again, guys. Don't know what. All right. Here we go. Okay. So. There we go. All right, so so now I'd like to just show the trivial proof for why we have exponentially soft amplitudes in the Lorentzian momenta. We start with these. We start with the classical string solution for closed strings. So there it is. There's dz bar x, as is familiar. And just one comment is that note that when the momenta did I break up again there?
Yeah.
All right, that's very, very odd. I don't know what is going on.
No, it's better.
Is that okay or not?
Yeah, that's great. Yeah, that's great.
All right, okay, fine. So it seems okay. Seems correlated with my full screen, which is crazy. But okay. Is it still okay or no?
Yeah, okay.
All right, good. All right, so just one little comment is that when the momenta are real, but independent of any signature, obviously, the dz bar of x is the complex conjugate of dz of x, right? So that's just the little point. Now we know that the classical string solution has to satisfy the Virasoro constraint. So that's the dzx squared, or dzx contracted with eta mu nu, has got to vanish. Remember that dzx is just the sum of pi mu over z minus zi. And so this basic fact that dzx squared vanishes, this is, I think, very well known to people who study scattering equations even recently and so on. This one beautiful fact that dx squared equals 0 encapsulates all the interesting formulas that we know are related to this problem. For instance, if you demand that dx mu, just as a vector, as a function of z, and z bar has no singularities at infinity, that forces the sum of all the momenta to add up to 0. If you demand that now dx squared, it's supposed to be 0, but in particular, it should have no double poles. Well, no double poles means that p squared should equal 0. No, automatically p squared equals 0 means that it can't be Euclidean. Of course, it could be Lorentzian, but in principle, it could be any other signature with some pluses and minuses. But anyway, we enforce masslessness. And finally, demanding that dx squared, again, which should be 0, but in particular has no single poles, tells me precisely the scattering equations. Okay, so any solution of our kinematic problem is in fact associated with some vector dx, a vector that's a function of z and z bar, which is null. This dx squared is equal to a 0. And furthermore, if I now integrate over z and z bar, dzx, dz bar x, contracted with eta mu nu, well, by the standard trivial electrostatics, that's just equal to the sum of Sij log the magnitude of Zi minus Dj, which is our action. And up to the factor of a half, which I dropped, there should be a minus a half here. Since dz bar of x is dz of x star, I can also rewrite this as the integral over zz bar with a minus a half of dzx mod squared, okay, contracted with the eta metric. And that's it. Now comes in a trivial but nice fact about Lorentzian kinematics. And this is where the Lorentzian business comes in. And here's the trivial fact. If you have some vector, some vector in Lorentzian signature, where v nu, eta mu nu is equal to 0, so you have a null vector, then v dot v star is always less than or equal to 0. And clearly this implies what we want, because we have exactly the situation where dzx dot dzx is 0, but our action is the integral of negative dzx star. And since v dot v star is negative, this action is positive. All right. So this simple Lorentzian fact is at the heart of what makes the action positive. And the trivial proof, write v as a plus ib, where a and b are real. So b squared equals 0 implies that a squared equals b squared, or a dot b equals 0. And now we can just decide, could a be time-like in Lorentzian kinematics? If a is time-like, so let's say, so a squared is positive in some frame, a looks like something in the 0 component and 0 everywhere else. But then since a dot b equals 0, we learned that b would have to have a 0 in that top component, but then b squared would have to be space-like. And we couldn't have that a squared equals b squared. So that's it. So we have to have that a squared is less than or equal to 0, not greater than or equal to 0. On the other hand, v dot b star is a squared plus b squared. And since a squared equals b squared, it's just 2 times a squared. And so since a squared is negative, v dot b star has got to be negative. Okay? So, and notice that the Lorentzian nature of the kinematics was crucial to this argument because if we are allowed to have more time-like directions up here, then a dot b equals 0 would not force us into demanding that a squared and b squared have different signs. Okay, so this argument crucially makes use of the Lorentzian kinematics. All right, so that's the really simple proof that on any solution of the scattering equations, on any solution of the Gross-Mendel equations, the action is positive, and therefore the amplitude should be exponentially soft. And the final comment I want to make is that the Lorentzian kinematics is actually overkill for this. We don't have to have Lorentzian kinematics for the amplitude to be exponentially soft. And let me just preface this by a very simple question. You can ask, suppose you're given a matrix of the dot products, you're given a matrix of the pi dot pj's. So you're given all the Mendel stamps. How could you decide whether these actually came from Lorentzian kinematics or not? And this is a very simple answer. That's just a close cousin of the Sylvester criterion for deciding whether a real symmetric matrix is positive, has all positive eigenvalues. Here, essentially, we want to have some real positive matrix that has an indefinite form, but with one minus sign and all the rest plus signs. It's actually, for this problem, it's slightly simpler to use all plus signature. Anyway, the answer is very simple and beautiful. It's when this matrix has all of its upper adjusted minors, the upper 1 by 1, 2 by 2, 3 by 3, and so on. All the upper adjusted minors have to be negative. So the first one is just 0. The next one is manifestly negative because it's negative p1 dot p2 squared. The next 3 by 3 one is non-trivial. The rest of them are non-trivial. And the claim is that this data is Lorentzian if and only if all these upper adjusted minors are negative. Now, there's a particular subset of all of these guys. Imagine that I order this matrix with the particles I, j, k, dot, dot, dot. And let me just look at this top 3 by 3 matrix, the first non-trivial guy. So the statement is that the determinant of this 3 by 3 matrix should be negative. That just says that the product of Sij, Sjk, and Ski should be less than or equal to 0. Again, this is for all plus, mostly plus. For mostly minus signature that many of us like better, this statement is that this matrix would have to have alternating signs for its determinants, and the sign here would therefore be flipped. Okay, but I'm going just for this little part, I'm just going to use the mostly plus because it's a little bit nicer. Okay, so this is the condition on Mandelstams in order to come from Lorentzian kinematics, but there's a particularly simple set of constraints that are actually secretly linear constraints. These look like nonlinear constraints. All these determinants look like nonlinear constraints, but there's secretly some that are actually a bunch of linear constraints. And it's what you can call the in-out cone. So let's say you have any 3 guys. Have we seen that we have to have Sij, Sjk, Ski is less than 0? By the way, for example, for 4-point scattering, that just says that S times T times U is less than 0, which means that at least two of ST and U have to have the same sign, and the other one, and that's indeed exactly what we're used to with all plus, with mostly plus on the constraints on STU. Well, it's trivial to see that if you apply these nonlinear relations that just tell you something about one of them having a different sign than the other 2, if you apply it to all 3 tuples that you can make, all IJKs, then that's equivalent to saying that you can divide the set of all indices in 2. 2 that you can call the in indices and the out indices that have the property that S in and S out are negative, and the ones that go between them, the S in outs, are positive. So even though you started off with what look like all these nonlinear constraints, all of these guys together are just turned into this set of linear constraints. And you see, these are exactly the naive constraints that you would have had if you just said in Lorentzian kinematics, I have some incoming particles with positive energy, some outgoing particles with negative energy. And just that statement tells you that the incoming Mandelstams are negative, again, in mostly plus signatures. The in-out ones are positive. So the outgoing ones are positive, the incoming ones are positive, the in-out ones are negative. So this is a subset of all the conditions that are needed to enforce that the data is Lorentzian. For the particular case of 4-particle scattering, it's all the constraints there are. There aren't any more of them, but for higher points, there are these extra nonlinear constraints that come from the higher determinants in this matrix. But it appears, at least experimentally, in what we've observed through the 6-point scattering, is that if you do solve the scattering equation, take the real part of the action, then all that matters is that you're in this in-out cone, and that suffices in order to guarantee that the action is positive and therefore that the amplitude is exponentially soft. So there are definitely regions where the amplitude is exponentially soft that's not Lorentzian. What seems special about the Lorentzian kinematics is that it's way positive. If we go back to this expression, it's not just that the full action is positive, it's just that this integrand, the world sheet Lagrangian, is positive in Lorentzian kinematics on the support of the solution of the scattering equations. That's clearly not necessary for the whole action to be positive. And at least experimentally, it appears that there is a sort of larger regime that's not just Lorentzian, where the amplitudes are still exponentially soft. And it would be interesting if these had some use or some meaning. All right, I think that's all I'll talk about. I won't say anything about the last subject, which was just advertising some open problems. But maybe I will just leave it at that and see if there are any questions. Thank you very much.
Okay, thanks, Nima, for that very nice talk. I'm sure there will be questions. So yes, are there any? Let's go in the room first.
Nima, that property you were talking about between the open and closed string and the double copy on the Gegenbauers.
Yes.
Is that trivially obvious, or?
Yes, that's basically trivially obvious. Yes. I mean, sorry. The fact that the open string residue, that the closed string residue is the square of the open string residue is pretty trivially obvious. Yes. Yeah, and in fact, the residue for the heterotic string is the product of the type 1 residue, the type 1 open residue and the bosonic open residue for the polynomials. What's a little more unobvious is that there's any nice analog of these contour integral formulas for the actual residues, and in fact the sort of contour integral formulas that we sort of naturally find are these triple contour integrals. I should also say that we don't need as I stressed, once you know that the open strings are positive, the closed strings will automatically the residues. I mean, the residues will actually be a positive. But amusingly, if you take these triple contour integral formulas, it's hard to use them directly to prove positivity. So we don't yet know what those triple contour integral formulas are good for. But we would like to somehow understand. I mean, the thing that is not at all obvious is why these expressions exist already for the open string. That's what I was stressing. You can go through this sort of like this 2-page argument. It's not very complicated, but still, you make sort of several not totally obvious moves, and you arrive at this completely symmetrical formula. This must come from somewhere. I would be very disappointed if there isn't some better, some different understanding for where this formula comes from. But again, just to stress what's surprising about it, it's surprising that this actual literal residue would have a nice representation. It's not the amplitude, it's the residue in this partial wave expansion that has this nice representation. And anyway, that's something that we were certainly looking for a long time. And essentially, Lorenz found this formula by an amazing long sequence of manipulations. I still have no idea how we found it. And then after he found it, we found this kind of shorter, but still not entirely conceptual explanation, which is what I was telling you today. But this is it's still to me a kind of a crazy formula. I have no idea why it exists, but it does exist, and it's something new about string amplitudes. You know, I'm kind of amazed that there's still new things about the 4-point string amplitude that we're learning. over 50 years after these formulas were first written down.
Any other questions in the room?
Can I ask you one question, Nima? So
Yes.
do you see, like for these residue formulas, you have this d smaller equal than 6. Do you think there's like something you're missing to fill up the gap to d equals d smaller than or equal to 6?
Yes, yes. I mean, yes, I think there's something missing. I don't know what it is. It seems not. It seems like this residue formula seems as kind of perfect as could be. I don't see any way to like deform it or modify it somehow to get another formula that might make positivity manifest. But I should say that again, the way that positivity is manifest still involves some observation. It's not like, aha, for sure it's positive for reason X. Okay, you write in this contour integral, then you have to see that the kernel in there has this very slightly clever arguments that these functions, 1 over log 1 minus z plus 1 over z, and positive expansion, and so on. Not every one of the steps is not difficult, but it's not some sort of clear conceptual explanation. And, you know, I should say that I think that this is to me, this has been a problem for a long time. I mean, I don't find the proof of the no-ghost theorem. I mean, all of this in principle is proven by the no-ghost theorem, but I don't find that the no-ghost theorem is an especially conceptual understanding. It's something cool you do this move, you do that move, you invent these operators, you know, but every time you see it, it's kind of a 2-page argument. And it's not trivial. It's a very non-trivial thing, and it's, you know, the proof of the no-ghost theorem played a starring role in Borchard's work on moonshine. You know, this is a beefy, non-trivial fact, so I think it's a weird thing to have such a beefy, non-trivial fact still not have a conceptual explanation. And anyway, I think we're seeing various avatars of the failure of having that conceptual explanation. So here we have some new formula for the residues, but still, it's not especially conceptual why it's positive, even for d less than or equal to a 6. But what I'm hoping is that maybe we can understand better directly where this formula comes from, and maybe that better direct understanding would suggest a better understanding for positivity in general.
Great, thanks for that. Now let's move to online. Are there any questions online for Nima?
I'm shocked anyone is still there, but anyway.
It's a long list according to my screen here.
Nima, I have a question for you.
Yes.
So you were describing your earlier work with Uten on motivating the sort of semi-uniqueness of the Virasoro-Shapiro amplitude.
Right.
Why did you take the ansatz that the denominators had to be just products of poles?
Well, I mean, whatever the denominator is, you can always combine everything under one giant factor. It's just a question of whether the numerator is simple or not. And,
right.
But I would say 2 things. One, you can always write it that way. The huge assumption was the assumption that the only things that you need, that the only zeros on the numerator are there to kill the bad poles. Of course, you could have gazillions of other zeros. That there's no reason that has to be true, but it is, I think, striking that if you just assume that that's true, you immediately land on the amplitude we know and love. And I think the other thing is that I also think that this sort of famous fact in string theory that we can't separate the channels from each other, right? That we can't that we can't do expansion in the sum over channels. This is not some magic only stringy thing. It's a property of the gravity amplitude already. The low energy gravity amplitude already has this amazing fact in it, as does the Yang-Mills amplitude. As of course, almost everyone in this audience knows, anyone who looked at the on-shell amplitudes knows this amazing fact. But you know, people who don't internalize the on-shell amplitudes may not recognize this amazing fact that you cannot separate the channels. That's the sort of deep fact of theories that need to be described by gate symmetry. So you guys all know this, but anyway, I think that also motivates a kind of parallel to that. There's a product structure in the field theory limit, so it's not unreasonable that there should be a product structure for the whole thing.
Okay, thanks.
Any other online questions? Okay, so I suggest we formally close the session there. So let's thank Nima again for that very nice talk. I'll remind people again of the Slack channel where you can ask questions, and presumably, Nima, you will engage with that in the coming days or something if people have more questions. But yes, let's look forward to the rest of the conference. And
Nima,
yeah.
don't forget there's this Slack channel if people have more questions for you.
Sure. Yeah. I will. Yeah.